Today, the work is really was based on my honors student. An honors student in the British system is like a master's student. So it's as if he did his thesis with me. And when he started his project, I was really skeptical. So I said, okay, let's have a safe path so that when you invariably going to fail, you still have the thesis. But he didn't, so it was good. So it turned out to be the one that was mistaken. So I'm always happy to be proven wrong when the student does things that goes beyond my expectations. So the talk today, I will start from almost the beginning of game theory. And I try to provide a possible alternative way to think about some problems. And if we have time, hopefully I can show why that this other way of thinking about problems is useful. Give us more insight. Okay. So the outline of the talk is I will first talk about modeling strategic interactions. I tell you what I mean by graph in this setup. I will introduce you the graphical approach. And I talk about what these graphs can tell us. Then I will briefly touch upon how this can be applied to evolutionary game theory, especially through a framework that allows us to predict the fixed points of some of these learning, they call them learning dynamics, that people use to emulate how agents learn in the environment. And I just bring the main concept back and talk about really specifically about the attractors of the replicator, which is one of these famous dynamics that people use to model the learning process of agents when they learn policies that has nice properties in a game setup. Okay, let's go and talk about modeling strategic interactions. It's a Goldilocks problem. There's always, like anything in the world, you live on a spectrum. You can have a very broad models. You can have very specific models. Obviously, broad models, they can't make any predictions, but they can be applied to anything. They are equally useless everywhere. Very specific models, they can make a lot of predictions, so they are specifically useless, if you can think about it. So you can never be silly thing. You have to be somewhere in the middle. And that's where we are aiming for. Now, this is the slide for Antoine. It's a very old-fashioned way of writing, which I like. The whole thing is that they apologize a lot that they haven't done everything right. I feel the same way. It's a bit fatalistic. Well, maybe you cannot question their reality. Now, there is an interesting Canadian connection where I found this passage is from this book by an academic out of Queens. So this guy, Donald Harmon Atkinson. If anyone is interested, I really recommend the book. Anyhow, a very brief history of game theory. People claim it goes way before 1944. The notions were around, but it's agreed that von Neumann and Morgenstern were the ones that formalized the framework in the book, The Theory of Game Economic Behavior. You can still buy, it is in print, which is crazy. You can still buy that book if you want to spend money on books. The way that they define the game is that the game consists of players, strategies, and payoffs for each player in each strategy combination. Think of the strategies are the actions that the players take, and the tuples of actions. So, for example, if there are two players, the pairs of actions, one for each of the players is called a profile. And then Nash extends the concept to the notion of a Nash equilibrium and proves that that notion exists in all games. The way that they define it is it's a profile where no player can improve their payoffs by a unilateral change of strategy. So they are in a Mexican standard. You can't move the game anything better. Now, the first half of the talk I'm going to do a bit of foreshadowing, is there are these ways of defining strategic games using preference relations. For example, this is my second Canadian connection. By the book by Osborne and Rubinstein. Osborne is at U of T in the School of Economics. And this book is a really good book, if anyone's interested. Anyways, in their book, they require each player's preference to induce a total order on all profile. So that's how you can abstract away the payoff. The payoff is a number. You can abstract it away, but replace it by this total order across all the possible strategy profile. And that is what is different to what I'm going to propose in the next 10 to 15 slides, is we don't require a total order, we require a partial order. Okay, now let's talk about two simple games. So the first game that I will talk about, and both of these games, the setup is like this: two players simultaneously place a coin on the table. So either it has a head side or a tail side. It's not a random game. You choose which side you're going to play. In the first game, which is called the coordination game, the aim of the players, both players want to match the choice of the other. So it's a coordination game. Both of the players, they get the best outcome if both of them play heads or both of them play tails. In the context, I mean, I'm a control engineer at least. That was my training. In the dynamical systems and control problems, this is similar to the question of head-on collision avoidance. If two cars are coming towards each other, you want both of them to turn in the same direction, right? Both of them turn right, so they evade each other, or left. There's another game. It's called matching pennies. It's a game of discoordination. In a matching pennies game, one of the players wants to match the other player's choice, but the other player wants to mismatch the player. Example of the dynamical setup of it is the head-on pursuit evasion. In a pursuit evasion game, is one, I mean, if you've heard of the homicidal chauffeur, you want to run over the other player. That's what it is. So if you are heading to the same direction, one of the players wants to turn right, and the other one, one of them wants to evade, the other one wants to intercept. So that's how you can think about it. The other example is the penalty shootouts in soccer. So you can think about it. So the goalkeeper wants to match the direction, the other one wants to evade. But they are not games mathematically, the way that I've described it here, based on the definitions that I introduced earlier. Because I didn't give you payoffs. And I didn't give you a total ordering, really. Okay? But it is intuitive. So we want to see if we can capture that intuition without assigning those payoffs and the ordering to the game. So let's just build utilities, which are those payoffs. That's how it would look like. Right? We call it a payoff table. It's a matrix game. There are two actions by each of the players. They either play heads or tail. And the first is the payoff of player one, payoff of the player two. So in a coordination game, and these numbers are first arbitrary as well, right? These numbers came out of nowhere. One doesn't mean anything. It can be 257, doesn't matter. So if they play, both of them play head, both of them get payoff one. If they don't match, they don't get anything. If both of them play tail, they get payoff one. In a matching penny, if they match, player one loses and player two wins. So that's how the assignments work. And if they don't match, the rewards are flipped. Okay. Now I'm going to introduce this concept of a response graph. Through these examples, I'm going to give you a construction of these discrete objects. Let's construct a graph whose vertices are all the possible strategy profiles. So there are 4 possible combinations. Let's put them as vertices. And I'm going to draw an edge, a directed edge, from one vertex to the other, only if there is one strategy that is different between those 2 vertices. So I'm not going to connect these 2 together because there are 2 strategies that flip, but I connected one that only differ in one strategy. We call them comparable profiles. And I draw the direction of the edge towards the one whose payoff is higher in that profile. For example, in this setup, the thing that differs is the choice of the second player, and the second player payoff is higher compared here to here. The same thing there as well. This payoff is higher, so the direction is that way. In the other way, the first player action is different, and this payoff is higher, so it goes there. In the matching penny scenario, in the first player gets a bigger payoff in the lower left vertex, so the edge is from the top to bottom. So really, response graphs, the word that we use, the phrase that we use in the first paper, capture the intuitive definition of the game that they explained. Now, in retrospect, it wasn't a good name. We only realized it after we started talking to a lot of people, and a better name would have been a preference graph. The reason that we realized it's not a good name, because the more that we could talk about response graph, people think about it's a turn-based game. It's not. It just captures the relationship between the choices of profile. It was a contraction of a longer term, a better response relation. There is a best response relations in game theory. It's a local version of that. Anyways, maybe if we continue working in this direction, we can slowly change the name to preference graph. Or if someone else starts using it and they start calling it preference graph and say that the name was stupid, I agree. The other thing that it does, the other thing that we are interested is the notion of equilibria, or equilibrium. These 2 games, the first game, this coordination game, has 2 pure equilibria and 1 mixed one. The other one only has a mixed one. So we were interested to see if we can even capture that notion. Just as a side note, a pure equilibrium is a profile that coincides with a very specific action. For example, if both players play this game, in this profile, so both of them play H, neither of them can unilaterally improve the payoff. They cannot do any better unilaterally. So that's a notion of an equilibrium. In this game, everyone can make it unilaterally better depending on wherever you are. So there is no pure Nash equilibrium. There is only one mixed one. Now, a mixed Nash equilibrium is when you allocate. I'm being a bit loose here, probabilities to your choices. So you play 50-50 heads or tails. You spring that into the way you make the decision. This is a more complicated example of the graph. The reason is, in a 2x2 graphs, that better response relation and the best response relation is always the same, because there is only 2 choices. So the one that is better is the best one as well. I just wanted to show that, yeah, in a graph that looks like this in a 3x3 2-player game, that's the complete. That would be the graph of interactions. You can draw it as a grid of 3x3, but then you have these edges that overlap. This is just really like pull the graph aside to be able to show the relationships a bit better. I leave checking if that graph is correct as an assignment, as a homework. So, really the point is that 2x2 games are easy to draw. That's why we stick to 2x2 games for the purpose of illustration. Now, I said equilibrium is important. The other thing that I want you to have in mind is playing at an equilibrium doesn't mean that we are playing optimally. If you think about optimization all the time, there's always this mistake that people make, right? It's not a mistake, this is the bias. So that's the question I always get. And someone might say, oh, what if it was 10 and 10, so they have to choose that action? No, they don't have to choose any action. It's a question of equilibrium. The aim of the analysis here is not about optimizing anything. It's about just being on the cusp of not losing. Anyways, pure and mixed Nash equilibria. Again, these notions, if you want to compute them, they differ in 3 key ways. There are different computational complexity consideration associated with calculating them. There are these questions of structural stability, because I said people use these dynamics to mimic the learning process of agents. There are these questions of how those dynamics behave. And there's a question of stability of the dynamics. For example, this vector field captures the flows of the replicator dynamic. One of these dynamics that is very popular in population game. And if you just see, for this particular graph, it's a game which is a coordination game. The flow goes to these 2 pure Nashes. And there is an unstable equilibrium smack in the middle, which corresponds to the mixed Nash equilibrium. And because it is really unstable, the sort of dynamics that we use to do the computations will never converge. So maybe there is a tendency towards having non-Nash solutions to games that are amenable to computation and still capture the idea behind it. Now, another piece of history is again out of von Neumann and Morgenstern's book. It says it's even conceivable that a physical quantity is a number up to any monotone transformation. This is the case for quantities for which only a natural relation greater exists and nothing else. It applies the notion of utility when this is based on the conventional idea of preference. So really a lot of it suggests that, and you can again think about it like that as well, a lot of these payoffs are made of numbers that try to capture some relationship of something better than the other from the perspective of the particular player. And that's the key, not the cardinal value of the payoff. Okay, let's look at the graph that you have. This is what we saw. It captures everything that you're interested in. So we can just forget about the payoff matrix. The numbers, as I said, from this perspective, doesn't matter. We only care about this greater relationship. So let's just get rid of the payoffs. The labels don't matter either. I can replace this with apples and oranges. The actual labels don't matter. So let's just abstract that away. So we end up with 2 graphs. And these are the graphs that we are interested in. So that's, we are using the principle, the Occam's razor principle. Get rid of anything that doesn't matter, at least from our point of view, right? So I'm going to define preference games. And that's how we define it. It's a game, it's just the response graph. This is how we define the family of preference games. And a solution concept that we are going to propose is the notion of a sync-connected component of the response graph. A sync-connected component of a graph is a subgraph that doesn't have any outgoing edge. So for this example, these two are the sync-connected components. There is no edge leaving them. For this other one, the whole thing is the sync-connected component. Sync components come with this other thing called the contents. The contents of the component, and I will revisit it again if we have time at the second half of the talk. The content of the component are all the sub-games with all pure profiles in that component. You're going to see this again, hopefully, if we have time. Okay, I said modeling is the Goldilocks problem. We said, okay, let's just, this numerical payoffs are fictitious stuff anyways, but they allow us to talk about Nash equilibrium, but at the same time, we don't know, the payoffs cannot be reliably known. Response graphs, we have abstracted away this node that needs to know cardinal values for payoffs, but the solution concept is a bit unknown. So that's where we are going to ask a question. They are engineering friendly. We show that they capture, these graphs capture some non-trivial facts about the game. And response graphs sometimes really can give us new predictions, improve competency. Some of the things we can do about the evolutionary learning in these in games as well. So what can they tell us? Okay, so let's look at the special case of two-player games. We have potential games and zero-sum games. They are very famous families of games. In potential games, payoff differences are representable by a single potential function of the strategy. Potential function has satisfied everything that we know about potential function. And the Nash equilibria that we get in a potential game, they are always pure. In zero-sum games, payoffs of both players add to zero in each of the profiles. So this is an example, they add up to zero everywhere. And Nash equilibrium is unique. It's a generic statement as well. So that these are the things that we know about these two types of games. But what graphs would we get in either of these cases? Let's just replace the matrices with the graphs that we have. This is a result due to Papa Dimitri. I should have put the reference there. People there doing this. There they talked about best response graphs. For potential games, best response graphs and the response graphs that we talk about are very closely related. So we can extend their results trivially to response graphs that we have. The response graphs of potential games are exactly the acyclic graphs. They pretty look like that. This is a potential game. And then we have this other result. The response graph of zero-sum games are exactly those that are acyclic after reversing the preferences of one of the players. Flip the order. So for example, in this case, if I flip, this happens after flipping the orders. This is now cyclic. If I flip these two orders, I end up with an acyclic direction. So what I talked about here is analogous to the relationship between potential and Hamiltonian dynamics. This flip of the ordering brings to mind some symplectic transformation of the signs. Okay, now we have these two archetypical games. We can use them to construct classes of games. So we have preference potential and preference zero-sum games. They are all the games that share the same response graph with any of the corresponding potential or zero-sum games. So they define an equivalent class. So a preference potential game would always have a singleton sync connected component. So they would have singleton sets. Preference zero-sum games always have a unique sync connected component. So for this example, the whole graph is the sync connected component. But for a bigger version of it, it might not be the whole graph. The key is that there will be only one unique one. For preference potential, it might be non-unique, but each of them will be a singleton. Okay. Now, if I go and look at all of the 2x2 games, and if I get rid of all the degenerate cases and symmetric cases and everything, these are the 4 graphs that we get. All 2x2 cases end up getting one of these 4 scenarios. This is the coordination graph, this is the matching penny graph, and these 2 are 2 other ones. Again, it's modular all the other symmetric. You can say there's a flipped version of it, but they are equivalent, right? Now, this is from Ecclesiastes. There's nothing new under the sun. It's just a new interpretation. Really. Now, just a refresher on you. The dominated strategy, what it means. If I have 2 strategies, A and B, we say B is dominated by A if there is at least one set of the other player's actions for which B gives a worse outcome than A. The other ones can be the same. So just dominated by the other action. Now, this is the main theorem of this paper, which we didn't know where to send it. We sent it to scientific reports, and it turns out to be a very expensive choice. We paid $4,000 after it got. I don't know why. Apparently, yeah, that's the price. But I will never do that again. But the statement is this. And I think it's a use that was really the crux of this paper. So we say if any strategy in a 2-player game does not take part in a matching pennies or coordination subgame, so it doesn't think of a big game, write it as a response graph, and look at one of the strategies. If that the strategy never shows up in any of the subgraphs that look like either this or this, then there is a dominated strategy. So you can chop, one of the strategies is dominated by your action, so you can get rid of, if you want to keep doing it, keep getting rid of the strategies that don't matter, this allows you to do it. And that's really where the corollary is. Any 2-player game that is preference potential and preference zero-sum is dominance solvable. This is the notion of getting rid of all the profiles that has a strategy that is dominated by another strategy. It shrinks the space that you can do. There's another corollary. It says if every 2x2 subgame of a 2-player game is dominant solvable, then the game is dominant solvable. So really, this is the key role that these 2 graphs play in characterizing an overall game. Okay, we have, good. We made it halfway, and we are at the halfway checkpoint. Payoffs are not always numbers. Nash equilibria are not usually predictive in this setup. And response graphs capture the intuitive description of a game in terms of preferences. Now, response graphs capture the dominance and pure Nash equilibria. And potential and zero-sum games have naturally expressed as graph properties, as I said, in terms of those subgraphs. And by thinking graphically, we can find new game theory results. For example, that matching penny coordination game is new because we are relating some game properties to some discrete math object properties. I'm going to talk next. I'm going to talk about sync components and show how they are connected to the long-run behavior of natural dynamics that are used to learn or simulate the learning process in a game. And I wanted to say something. All right, now let's see what we can, how this can be applied to evolutionary game theory. So a big question that we have is in multi-agent learning, is when a collection of agents learn in a competitive environment, what strategies do they learn? That's we are interested in. And when a collection of populations of species evolve in a competitive environment, what strategies do they evolve? They are closely related, depending on your point of view. So again, foreshadowing. The key is that if we think of the learning as a dynamical system, you're interested in its, I am going to say something is wrong, but it helps us understand what I'm going to say. It's a question of fixed points. But what I'm going to show is that it's not always a fixed point, but that's the key. Where does the dynamic go to in the long run? Do we always need to run the dynamic and just wait until it gets somewhere? Or can we predict where it's going to go by just looking at the structure of the problem? So that's the structural property that you're after. Is it possible or not? Okay. So the dynamic that I'm going to get has motivated us is the replicator dynamic. It's a common dynamic used to model learning in agents. It came out of a paper in the 70s. It is very closely related to Lotka-Volterra dynamics. So it's the generalization of that. So in a two-player game, each player might have n strategies. And let's call X and Y to be some n-dimensional vectors whose S entry capture the probability of playing a strategy. So I have n strategies, and I want to assign probabilities of which strategy I'm going to play. The replicator dynamic models the learning process of the players, and it looks like this. Each of these probabilities, forget about this for the time being. This corresponds to the average payoff given the current choices of the other player, subtracted by the expected payoff when both players play together. This is how the dynamics work. And A is the payoff matrix. And in what follows, we argue that a lot can be said without knowing A exactly. Again, A, the weights currently treated, A is the payoff matrix, has the cardinal values as elements of it. And in the first half of the talk, I went on and on about that we don't need those numbers to predict a lot of the properties. And this is where it's going to come in. We don't need to know exactly the numbers. We just need to know if something's bigger than the other one. And what can we say? So again, it's a structural question. Okay, so what does a long run outcome look like? So would all the flow go to one point? It's not the case all the time. Would it go and enter a limit cycle? Or would it go into a set and just mixes inside that set? So it's a notion of the attractor. So what we are going to limit ourselves is, we limit ourselves to attractors to capture the whole bunch of types of the behaviors you get out of in a dynamical system. Think of the attractors as sets that you don't are forward invariant. You don't leave them. You stay inside them, and they capture the behaviors that you're interested in. They can contain a fixed point inside them, and then the fixed point becomes the attractor. Okay. So the main concept we are going to use to answer these questions, they come out of the replicator dynamic, think of chain components and the response graph, which is what I spent the first half of the talk talking about. So the replicator dynamic, as I said, is super famous. It is related to this multiplicative weight algorithm in layering theory. This is the discrete time version of the replicator dynamic. Chain components. Sync chain components, it was proposed by these people as a notion of long-run outcome. I will talk about them a bit. And then the response graph is just the abstraction of the strategic relationship. This is what we saw. We don't need to do it. Replicator dynamics look like this. Again, current payoff for strategy number S, the S strategy, the current average payoff, updated. That's how it looks like. And these are the sort of vector fields you get when you use the replicator dynamic in two games. Now let's see if I can. I want you to remember a picture earlier. Remember that picture? I talked about sync chain components in a discrete object. And now look at these two vector fields. Which one is which? This is the preference graph, and again, this is the matching penny one, right? Yeah, this coordination. So that's where this is the reason that got us thinking in the first place. Looks like I can predict how these dynamics behave by just looking at the graph. We wanted to formalize that relationship. This whole thing was the sync component, the dynamic mixes in it. Mixing is not a technical term, but you know what I mean. These two have two singletons as the sync component, and the flow goes to these 2 points. Obviously, we don't know where they go because that depends on the initial condition, but we know these are the 2 possibilities. We're just looking at the graph. Chain components. Okay. Does anyone remember homoclinic orbits and heteroclinic orbits? Don't worry about it. Because I wanted, yeah. So there is this notion of epsilon T chain as a sequence of points, so let's have a sequence of points that it's like I have flows of my dynamical system that almost are in the neighborhood of each other. I call all of them a chain. This was a notion that was introduced by this guy called Tunley in the late 70s. And his aim was to capture the behavior of ODE solvers on computers, right? Because when you solve a continuous time flow, you're never exactly on the same flow. There are numerical errors. And that was the notion that he wanted to use to capture those sort of behaviors. But it is useful for other reasons, right? Does anyone remember the Lorentz attractor? It looks like, okay, it looks like a periodic orbit, but it's not. It's a dynamic that goes and wiggles around, but keeps repeating the same thing. But if you just look at it, you think it's the same orbit, but it's never the same orbit. Using this methodology, you can almost fudge it and say it's the same orbit, because there you can always jump infinitesimally to a different path. Okay? So it allows us to really step away from getting bogged down in differentiating between all these nuanced dynamical system behaviors. As a result, we can introduce this notion of chain component. We can define this notion of a pseudo orbit, which is not exactly an orbit. Orbit is when you start from somewhere, you end up there. Pseudo orbit Start from somewhere, you end up somewhere close to it. We can define these sets of points that are close to each other under this wishy-washy way of me explaining it. So you can always almost arrive at the point that you're interested in. It's not exactly reachable, it's like an epsilon reachability question. Now, why did I say that? Because then all of these things belong to the same chain components. Even if I have multiple concentric orbits, if the set of the orbits is dense, I can pretend I can infinitesimally jump from one orbit to another orbit to another orbit to cover the whole area. So that's what we good from that perspective. It allows us to put things in classes. The problem is that, as I said, 2x2 games is fine, but the picture is not always so simple. So that's this other work in algorithmic learning theory a couple of months ago now, in February. We can prove existence. So we can say each sync-connected component, which is a graphical object, everything red in the next couple of slides is a discrete mathematical object. Everything blue is a dynamical systems point of view. So each sync-connected component of the response graph is contained in a chain component of the replicator dynamic. At least one of those is a sync chain component. So this is, think of it like that, the attractor. So if I have my graphical object, I go and embed it in your favorite, let's say, Euclidean space. It's really in a simplex, but right? And I assign points to the edges. The graphical object will live inside the attractor. And then there is this notion of content. Content is the support of that sync component. Yeah, so this is the content now. So the content of each sync connected component gives us a lower bound of the attractor. We cannot eat. That's the result. I have a discrete math object. I go and embed it in space. I use that embedding to construct a dense set. That dense set is an inner approximation of the attractor of my learning dynamics. We have a conjecture. The conjecture is that the content thing, I'm going to skip that. I will tell you what I mean there. It's almost always the attractor. I say generically exactly, because we have found one weird counterexample, which if we perturb it a tiny bit, the counterexample goes away. So that's why it's a generic statement. Almost everywhere else, we haven't been able to find a counterexample. What it really means is that at least the long-run behavior of the replicator depends on the discrete preferences alone. So the actual values don't matter as long as doesn't matter if it is 1 or 1.1, as long as the other preference is more than 1.1. So it gives you a bit of, in your modeling question, you don't need to capture the preferences exactly. It's not sensitive to the actual values as long as you get the relationships right. So when these two objects are exactly the same, when the sync connected component is a subgame, so if I can construct a complete subgame out of that set, they are the same. In the terms of the potential games, that's the case. Any 2x(n) game, so one player has two strategies, the other player has n. Any strongly connected game, or when the game is zero-sum, which is this thing that we are sending it to the neural. An earlier version of it, we sent it to the Economic and Computation Conference. I was expecting us to get really hammered, but we weren't. But we didn't get in, but at least they were nice about it. So. And they read the paper, which is really rare. Okay, so the outcome of this motivated learning can be defined as sync chain components. And we can show that they exist, and they contain the content of the sync components of the response graph, which is again this object that we poorly named. And if the conjecture is true, the long-run behavior of the replicator is defined only by performance. Now, this is my ad. I'm looking for a PhD student. We pay way more than here. And that's starting there. And the postdoc salaries are way more than here too. So anyways, contact me if you're interested.